So those are the details of the course. Let's shift now to this second portion of this topic, where we consider this simple question: what is calculus? Some of you have never taken a calculus class before, so you may be wondering what you're getting yourself into, and others of you have taken a calculus class before, but may not really remember what it was that you were supposed to be learning. So let's go ahead and define what calculus is. Calculus is simply the study of change. So in particular, we're looking at how one quantity changes as another quantity is allowed to change. We'll get into this more in a minute, but this is really just the crux of what we're going to be studying. We really want to examine how quantities, how mathematical functions change. By the way, these two gentlemen here are Newton and Leibniz. They're the two men who are credited with discovering the field of calculus back in the 1600s. A great story. They were bitter rivals at the time, and there's a really interesting history behind the discovery of calculus that you might want to explore on your own sometime. So let's take a look at some examples. So let's take a look at an example. In the picture that you see here, we have what's called a profit curve. Now, notice that on the horizontal axis, sometimes called the x-axis, we have quantity. So this is quantity of items sold and produced. So what we're imagining here is a company that is designing a new product that it wants to take to market, and it is trying to determine how many items it should sell, what price it should charge in order to, let's say, maximize profits. So we're looking at quantity of items that are sold and produced on the horizontal axis, and on the vertical axis we have total dollars of profit. So what we want to pay attention to here is the idea of this hypothetical situation. We haven't produced or sold any items yet. We're doing an analysis of what would happen if we had certain information about how many items were sold and produced. So that's the setup. Let's take a look at a particular point on the curve, let's say when 20 items have been sold and produced. So down here on the horizontal axis, you can see there's 20 items that are sold and produced. And this graph tells us very clearly by looking over at the vertical axis that when we sell 20 items, when we produce 20 items, we will make about $3,000 in profit. Now, the graph tells us that just by looking at it. But in calculus, the question that we really want to pay attention to is, at that particular point on the graph, when 20 items have been sold and produced, let's say, how fast are the profits changing at that point? Now, we can see from the graph that the profits are rising, but the question is, how fast? Are the profits going up by $3 per item sold and produced, or by $30 per item sold and produced? And how do we know what that is? So the way we measure that in mathematics is by drawing a line that is just tangent to that point on the curve. So this is called a tangent line. It's a line that just barely touches the curve at that particular point. So it does not cut the curve or intersect the curve. It nicely sits on the curve. And if we can draw this curve accurately without any error whatsoever, then we can answer the question about how fast the profits are changing by computing the slope of the line. So most of you have done slope calculations before. And so what calculus boils down to is answering a very simple question. If I pick a point on a curve and I draw a line tangent to that point on that curve, what is the slope of the line? If I can answer that question, I can answer virtually every question that is important in terms of calculus in this course. So half of calculus is determining the slope of a line that is tangent to a curve. The other half of calculus has to do with calculating the area that is trapped between a curve and a horizontal axis, the x-axis. And so another way to say this is, how does change accumulate? And we're not going to get into this a whole lot. I'm just going to give this to you sort of as some background. But essentially, you can see over here on the left side, the task at hand would be to compute the exact area that's trapped between the curve and the x-axis without any error whatsoever. Now, because this is a curve and not a straight line, that makes this task potentially very difficult, and it took literally hundreds of years for mathematicians to figure this out, and calculus is what did the job. Now, in a business or economics type of setting, one of the more common applications of this part of calculus has to do with probability distributions. So if you've seen statistics before, you'll probably recognize this as a bell curve, or what we call a normal curve. And on the horizontal axis, you have numbers from 0 to 3 and 0 to -3, and those are standard deviations. And so the picture that you see here on the right is shaded between -1 standard deviation from the mean and +1 standard deviation from the mean. And so the area there represents the probability that your randomly drawn data point is within 1 standard deviation. So when you take your statistics courses, or when you took your statistics courses, you did a lot of this. You probably saw tables in the back of a statistics book that calculated probabilities for you. All those tables are generated by using calculus, the other half of calculus, and doing this kind of area computation. So that's the other half of calculus. We won't do much of that in this course based on the input I've received from other instructors and other professors. And so we'll focus on the slopes of tangent lines. So that wraps up the quick introduction to the course and a quick introduction to what calculus is. We'll now move on to the meat of this particular topic, which is basically an algebra review, but we're going to do it in a slightly different way. We're going to do it by reviewing some basic ideas of linear and quadratic functions by looking at business-related functions like demand and revenue and cost and profit. We will also introduce some of the software that we'll be using in this course to do some of the more complex calculations as well. So let's go ahead and get started. So let's start by looking at our objectives, our mathematical objectives for this particular topic. The first two things we want to do are review basic linear functions and basic quadratic functions. So I will assume you have seen this before, but we'll do a really quick review just to sort of jog your memory. And then if you need more review, you'll want to go back to something like Forgotten Algebra by Barbara Lee. In this particular topic, we will do this kind of review by looking at cost functions in a business setting. We'll then move to demand functions and what they mean. We'll then look at the relationship between a revenue function and a demand function. And then finally, we'll put all of that together to look at profit functions. All right, so let's go ahead and start with a linear function. So a linear function is a function of the form y equals mx plus b. Now, what we want to keep in mind here is that y and f of x are interchangeable. So this notation f of x does not mean f times x. Instead, it means that y is a function of x. So inside of the parentheses, when we use function notation like this, the variable that's inside is always on the horizontal axis, and we call that the independent variable. It's independent in the sense that it gets to change or vary. The other variable, in this case the y, is always on the vertical axis, and we call that the dependent variable. So we say that y is a function of x, or in this case, another way of saying it is y is equal to f of x. So y depends on x. So in a linear function, it has this general form. You can see here y is equal to mx plus b. And the first piece we want to look at is the m. So the slope of the line is denoted by the letter m. So m represents the slope of the line, and there's different ways that people think about this. One way is to think about this as the change in the y over the change in the x. So how far up do you go in the y direction when you move a certain distance in the x direction? Other people learn this by thinking about rise over run. In other words, how much does the line rise as it runs in the horizontal direction? And then the formula that we use when we're trying to actually do the computation and we're given 2 points is this here, It's y2 minus y1 all divided by x2 minus x1. So we're going to see an example of this in a moment, but this is the basic notation, and this is what we've seen before when we've studied lines. The second part of a linear function is the b portion, and the b portion is what we call the y-intercept. It is the point where that line crosses or intercepts the y-axis. So let's take a look at an example of this in picture form so we can see how this all fits together. So here's an example of a very simple line. We have y is equal to 2/3 of x plus 4. So let's take a look at the point that you can see here on the graph in the red dot. And let's see what happens as we make our way from this point on the line to another point on the line. So I'm going to start at this point on the line, and I'm going to move over just a little bit in the horizontal direction to the right here, in the positive direction. And then I'm going to move back up to the line to a new point. Now, because the slope of the line is 2/3 or 2/3, we know that to get from one point on the line to the next point on the line, that the change in x has to be +3. Positive because it moves to the right. When we move 3 units to the right on the x-axis, to get back onto the line, we have to move 2 units to the right. So the change in y, or delta y, is +2, and it's positive because we're going up. So that's the idea of a slope. As you move from one point on the line to another point on the line, the ratio of the distance of the change in y over the change in x will always be 2/3. Also, we can see that the y-intercept is at 4, so this is where the line intercepts the y-axis, and you can see the b value there at the end of the equation corresponds to what you see on the graph. So this is the basic idea of slope and intercept.